Okay, let's get started. We have 14 people now. Let's get started. I'm going to share my screen. Can you guys see my screen?
Yeah. Yes.
Okay, cool. So today we will keep talking about stack-based buffer overflow, and what we discussed today could be a little bit challenging. So we probably will spend a little bit more time on the homework than the first 2 weeks for this week and also the week after. We will talk about a little bit about the homework. So first of all, in last class, we started talking about buffer overflow. Buffer overflow, especially stack buffer overflow, is actually a well-defined problem. So what we are studying here for the next week and also previous weeks, uh, it's very hard to pull off in real-world systems now. But this is like the beginning of all the system security, software security. So understanding every step here is very important for us to understand more advanced attack techniques like return-oriented programming. So you will notice that no matter the buffer overflow we're doing this week, last week, and also in the future, the return-oriented programming, there is one key instruction, is that return. It's because there is a return address on the stack, and that return, how that return instruction works. That's how we can exploit those vulnerabilities. So last week we talked about where variables are placed on the program's address space. More importantly, the return address of the caller and the caller's string pointers are also stored on stack. I talked a little bit that this is kind of like the problem because we are putting some control information, some metadata together with data. On the stack, we have local variables. Those are pure data. We don't use them as address. Of course, if they're pointers, they're still address, but they're data. Then there are some control information, flow control information, such as return address. Those are very sensitive things. So, but we mix them together in the same channel. In the same channel, we have data, we have control information, and when we write data, we can overwrite the control information. That's the main problem here. If we can separate it into different channels, then probably we can solve the problem. We also learned that some calling conventions, and also you tested the fast core calling convention for homework. We also talked about how you can overwrite local variables on the stack if that local variable is at a higher address than the buffer you can overwrite. We also tried to override the return address to call a function, add the process address space. Today we are going to do something more difficult than that. First of all, let's quickly go through the homework 2. Homework 2, the first one, I ask you guys to find the addresses for global and local variables. You should find out that local variables are on stack, the parameters are on stack, the return address is in EAX, and the global variables is in DSS or data section. The second one is the fast call. So based on the homework you submit, I can see that all of you find out we are using ECX to pass the parameter in x86 for fast call. The third one, this is something you need to remember. If you remember this, it will make your job much easier when you debug and try to understand things going on the stack. But this one is a 32-bit. So EBX points to the saved EBS, plus 4 is the return address, plus 8 is the first argument, plus C is 12, so it's a second argument, or anything below that would be the current function's stack frame. So it's probably something like a local variables. Also, you need to remember the prologue and epilogue. After that, task 5, I ask you to Basically, the task 5, the idea is to um, find out that in 64-bit version, we use registers, especially the first six parameters. We are only using registers. We are not using the stack. That actually will affect security a lot. We will talk about calling return to a function at the address space with parameters today, and you can see that that approach only work for 32-bit version, will not work for 64-bit version, because the 64-bit version you do not put the parameters on the stack, you put them on the registers, right? So how do you do that if you want to pull off that attack? That one we will rely on some new technique. We have to rely on return-oriented programming, which we will discuss at the second half of the class. Then those two, I think it's easy to do. You can just follow what I did there. The last one is a buffer overflow to crack a program, and there was a local variable, and that local variable compare with a fixed value, dead beef. So what you need to do is to calculate the distance between the beginning of the buffer and the saved EBP. From there, you can craft that exploit. So basically, it should be the size of the distance between the buff and the saved EBP plus 4, which is the saved EBP, then plus 4, which is the function you are going to call. No, this one is just this one is just local variable. Okay, so I was talking about today's homework. Okay, so that's how we quickly go through the homework. Today, we actually have a lot to discuss. I'm not sure how much we can cover, and some of the materials we discussed today will be a little bit tricky to understand. So just interrupt me if you have any questions. Okay. First, we will try to overwrite the return address on the stack and return to a function with parameters. We covered this a little bit last week, but seems like people are quite confused. So I made more animations there to carefully explain what's going on the stack, and hopefully people can understand from there. Then we can discuss if we can we can return to a function with parameters. Can we return to multiple functions? That would be fun, right? So what if we can build a chain of functions to return to? Is that possible? Or if those functions take parameters, can we do that, right? Those are interesting questions we are going to figure out today. Then we will talk about how we can overflow with some shellcode. You will see for the first time a 64-bit shellcode and a 32-bit shellcode, and you will understand what shellcode is, and you will understand each instructions it execute. So it's not that scary at all. If we have time, we will also do overflow with shellcode and put the shellcode in environment variables. And I guess today we will not have time to talk about return to libc. But return to libc is highly related to the first two bullets we're talking about. The first two bullets, we're talking about return to a function we developed in our address space. Return to libc is actually the same thing. So libc is linked to your program, dynamically or statically, doesn't really matter. So it is in your program's address space. So technically, it's someplace you can jump to or return to. But for return to libc, maybe next week, we will only talk about the 32-bit version, like I said. The main problem is the parameter. When you call that, you need to think about how to put the parameters there. But for 32-bit, we can easily put the parameter on the stack. But for 64-bit, we need to put the parameter on the registers. When you overwrite stack, there's no way you overwrite registers. So you need to find other ways to overwrite registers, to change values in registers. That we will rely to something called ROP, return-oriented programming, which we will study at the second half of this class. Okay, before we go forward, let me remind you one more time the stack. So imagine this is a high address, this is no address, and we usually call a function's stack frame is where the EBP points to and where the ESP points to is something between the EBP and the ESP. The EBP in any function point to the previous function's saved EBP, and lower than that, we have all kinds of local variables. Higher than that, we have a return address and arguments. For 32-bit version, we are using EBP, so every unit here is 4 bytes. For the 64-bit version, we're using RBP, so all the elements here are 8 bytes. And also we don't have arguments here anymore. The return address is 8 bytes, the saved RBP is also 8 bytes. So that's the main difference between 32-bit version and the 64-bit version. So for some other architectures, and for example, ARM, it's a little bit similar. Could be a little bit different. For example, ARM, there is a special register ARR for you to store the return address. So the return address is not necessarily stored on the stack. But most cases, if you want to call another function, you still need to push that onto the stack. So it's a very similar structure. But some of them may not have the saved EBP. Some architecture may not have the saved EBP or something different. Or some architecture may have a little bit more information here. That depends on different architecture. But the principle is the same. So as long as you understand that, if you switch to other architectures, you should be able to pick up easily. So if we move something from a lower address at EBP to EAX, we're just accessing a local variable. Or if you use the instruction node effective address, LEA, we're actually getting the local variable's address. And if we store argument, or maybe store is a little bit confusing here. Maybe if they were accessing the argument from the caller, then we're doing EBP plus something, or EBP could be plus 8, could be 6. And the positive index over ESP could be argument, could be a function argument to the core E. So the core E here I'm talking about, the function we are in is going to call something. And that function, and now we're the caller. The caller, we may pass some argument to the core E, and we may use ESP to do the indexing. For the 64-bit version, very similar. Only the argument part, we're not using stack anymore. We are using this registers, RDX, for the first register directly. So if we set up parameters, we also do not push. We just move the parameters to the EDI or other registers. Okay, so one thing I really like to do is whenever we do some kind of attack, I always like to list all the conditions we depend on to pull off that attack. I find this is a very useful exercise for me to develop or to think about what kind of defense we can take. So you can come up with many conditions that we pull off the attack. But if you just take out one condition, the attack may not work. You make the attack a little bit harder to pull off. Some of them can be bypassed, some of them cannot be bypassed. For example, last class, we tried to overwrite the return address on the stack. And when the return instruction is executed, we go to that function whose address we overwrite on the stack. So think about how we can actually pull off this attack. The first condition is the function we want to call or we want to return to is already in the address space, right? In this case, we're not putting new function there. The function is already there. If the function is not there, we cannot call it, that's for sure. Then the second one is we need the ability to overwrite the return address on the stack, which means we need we need a buffer overflow. There could be a string copy, gets, those functions, or even fgets or string uncopy. If they do not set up the correct limit size there, you can still override things you're not supposed to override, right? So that the second ability is super important. The third one is you also need to know the address of the function you need to jump to. Sometimes you don't need to know the exact address, but for last week, what we did is actually you needed the exact address. Okay, you cannot even be 1 byte off. If you get 1 byte off, what will happen? The CPU will retrieve instructions from 1 byte off, either higher or lower, then interpret that 4 bytes or whatever bytes, number of bytes as an instruction. And that will be a different instruction as the beginning of the actual function starts. And that instruction will do weird things. We're guaranteed to fail at some point. Well, there's no way you jump to some garbage and keep executing. Right? There's no way. Right? Eventually, it will generate some kind of exception, trigger some fault. So you also need to know the exact address of the destination function. For the last class, I cheat a little bit. In the program, the vulnerable program, I just print out where that function is, right? In other cases, you probably can use a static analysis to find out where that is, but there are other protections there. And also, you probably need the ability to set up arguments if the function you're calling needs arguments. So now let's change our black hat a little bit to white hat. Think as a defender. How can we defeat this kind of attack? The first one, the function is already in the address space. How can we defeat something like that? Maybe as a defender at a compiler level, we can remove functions that will never be used, right? So there will be, if there is a backdoor, then we remove that because no one is explicitly calling for the backdoor. At compiler level, we do program analysis to remove that. Or the second one is the ability to override a return address. There are many things we will discuss starting from next week is trying to protect this. How do we stop this from happening? For example, now when you already say that when you compile those vulnerable programs, the GCC compiler always tell you, you should never use the function like gets or function like a string copy. You should never use that. GCC doesn't really forbid you from using that, but it always tell you, you should not use it. Okay, so if no one uses those vulnerable functions, maybe there is no buffer overflow vulnerability, right? That's the first thing. The second thing is other functions, even though they like string uncopy, there could still be vulnerabilities. Depends on if the developers give it the right values. The third one is knowing the address of the destination function. You have to know where you jump to or return to. So how do we make that hard? So one of the technique is called address space layout randomization. So when a program is loaded, the loader, basically part of the kernel, will make sure that each time it loads a program, it will load all the modules like text, stack, global variables, load them at different address. So even if you and your friend have the same computer, you are running the same program, your program have a different memory map than your friend's computer. So if you are trying to hack things on your own computer and get the address, that address will not work on your friend's computer. So this is not really a thing, I guess 15 years ago. So this is something we have in the last maybe 15 or 10 years to randomize things, to make things more secure. So this is, so for all the attacks in the future, I will try to summarize the conditions we have to pull it off and say how we can defeat those kind of attacks. So I told you there are some insecure say functions like a string copy, memory copy, gets, but those are the functions you're not supposed to use anymore. By removing those functions, our current uh, software security is in a much better state. What we're learning for, like I said, what we're learning this week, last week, and maybe the week after, a lot of what we're doing is ancient art. Okay, it's not going to work on real world computers. If you check the make file I have for all the programs we do, you can see I add a lot of parameters here. For example, let's say where are we? So last week, which one did we do? System security code. So we were doing overwritten 3 last week, I believe. So you can see here, let's do the kind of the make file. As you can see, the make file I have here, I give it many different parameters to GCC, different flags. So one of the flag here is called the no stack protector. So to make it work, I have to give this, to make this attack possible, I have to give this flag to stop GCC generate some protections. So the other one we're doing today, for example, return 4, if you check the make file, you can see I give it many different flags. The first one is no stack protector. The second one is executable stack. So this one will make the stack executable. So because today we're going to put code in the stack and execute from there. But when you compile a program right now, by default, you're not giving those flags. Those flags are disabling those protections. Okay. So which means now when you compile something, you just do a GCC, then your program is automatically protected by those techniques. Of course, those techniques are not perfect. There are ways to bypass it, but they are built in compiler to protect, and they raise the bars for this kind of buffer overflow very, very high. So that's why what we're doing here, even though today we may have some time to do a war game online, and you can see that that is also kind of like a very old machine. In modern machines, it's very difficult. And also remember, we also disabled address-based layout randomization here. That echo 0 thing was to disable that. Is everyone still following? So for the graduate student, could you please turn on your camera so I can get a feeling what you're doing there? Cool. Okay, let's keep going. So the first topic we are going to cover today is return to a function with parameters. This is what we covered a little bit last week, and I believe it was a little bit confusing. So the program we have here is the overflow return to. As you can see, the main function is print out the address of the print secret. So then in this function, it takes one parameter argument, and it's a fixed value. After that, it will print out either congratulations or I pity the fool, then exit. And this function print secret is not called by anyone. So here, this one is not going to call this function. So here we're only getting the address of this function, print it out. Then we're calling the variable function. The variable function will have a buffer, which is 6 bytes, but it's not necessarily 6 bytes. The compiler at binary level, because the compiler may add some padding. We talked about this. Then there is a variable function gets, which will get input from standard in and override the buffer, and also everything above the buffer, it will return. It will not do anything. It will not call any other functions. To make it a little bit easier, we disable address space layout randomization. So let's take a look at the stack and try to understand how it works to say how we can call this function with this parameter. As you can see here, let's assume right now we are here. We are at gets, right? So we know buffer is somewhere below saved EBP, and we know the EBP right now points to here. The ESP is somewhere here, doesn't really matter. It's somewhere lower, okay? We're not using it anyway. And above the saved EBP, we have the return address. So after this function, what happened is everything from here to everything above, like very, very high, we can overwrite. We do not only, we can overwrite more than those 3 units. We can overwrite everything above that, but we probably don't need to. Because we want to call this function print secret, what we want to do is we want to change the return address to the address of print secret. The saved EBP value is not really very important at this moment. So let's say we just put all A's there. It's just garbage, doesn't really matter. Then let's see how this will change. So when we do a return 0 here, what we're actually doing is there are 3 instructions. The first one is move EBP to ESP. So both EBP and ESP will point to the saved EBP, which we just overwrite, which is 4X. Then we will pop EBP. So this instruction will change both registers, EBP and ESP. Because we do pop, whenever you do a pop, ESP will increment 4, right? So ESP now will point to the return address, which we have overwritten to the address of print secret. And the EBP will also be changed because we're popping the data at the top of the stack to EBP. So EBP now points to, the value of EBP is 4X. So after that, we have the return instruction. So what the return instruction does is the return instruction doesn't change any other registers, but only 2. It actually changes 2 registers. It doesn't change EBP. After we do this return, EBP is still the same, 4X. However, ESP is changed. So return implies a pop there. The return actually is popping top of the stack to EIP. So what happens after this instruction is ESP will increment by 4. So ESP now points to this green unit. However, the address of print secret is put back to EIP. So you can imagine this is how we balance the stack, right? So that before we call this function, the ESP actually points here. Because a call instruction pushes the address, return address here. So before the call instruction, the ESP points here. So no matter what you execute, no matter how many functions you keep calling, recursively calling in this call E, eventually the ESP is supposed to go back to the original place. So the stack is balanced. Go to the original place before you call this function. So after this return address, after this return instruction, the print secret function address goes to EIP, and the ESP points to the green unit. So the problem here is we are returning to a function that we didn't get here by calling it, right? Now we're returning to print secret. We're returning to a function. Previously, we're supposed to return to somewhere here. No, this is still part of another function. Now we're not returning to the middle of the main function. We're returning to the beginning of the print secret function, which means here in the main function, we did the product. We already run the prolog instructions. Then we call this, we do this. Okay. Now we're returning to print secret. We're going to run the prologs of print secret again. So the stack will not be balanced anymore. Okay. So that's the key here. That's the problem we can make this happen. Let's say, okay, at this point, we are in the print secret function. The beginning of it is a prolog, and the first instruction is push EBP. So EBP, we have a value here, which is 4x. Now ESP pointer here. Now we're going to push it, which means ESP were decrements 4 bytes and put 4x here, which means we will overwrite this instruction, will overwrite what we just overwrite there, okay? So here, we will also have 4x. This is because we pushed EBP. Now ESP points to here, we have 4x. Then we move ESP to EBP. So both EBP and ESP points to the 4x. And we are in this function print secret. So print secret now considers this part as its own saved EBP, which means this part will be considered by print secret as the return value when it returns. But in this case, we don't really return because there's an exit. We don't need to return it because we're only calling this function. So if this part is considered as saved EBP by print secret, then these 4 bytes are considered as return address by this function, and upper than that, we have the parameter 1, right? And you can see that then this is very easy for us to call this function or return to this function with parameters. This is what we do. At the beginning, we're only overwriting those 12 bytes. Oh, no, not more than 12 bytes. We're only overwriting, let's say, those 8 bytes, right? Starting from saved EBP. We can overwrite more than that, okay? We still override that old saved EBP. Then we put the address of print secret. Then this part will be considered as what? As the return address for the print secret. So here we're not calling another secret, another function. So it doesn't matter. So we don't put anything here because there's no return anyway. There's an exit. But we can put the parameter on top of this. So if we overwrite these 16 bytes, we will be able to call the return to the print secret function with a parameter. Okay, does that make sense? Any questions here? Does that make sense? Okay, good. Okay.
I have a question, if you don't mind.
Yeah.
Can you just quickly go into a little detail about what this Python exploit exactly is doing?
Which one?
Just any of them. Like I made it work on the homework and I followed along.
Oh, you're talking about
that it's the key to do everything, but how exactly does that work?
Oh, you're talking about, for example, you're talking about the syntax here? Maybe
Yeah.
the syntax here that will be confusing? Okay. Yeah. So first of all, something you notice here, this is something called a pipe, right? So this bar here is something called pipe. So it will connect the 2 programs together. It will transfer the output of the first part to the standard input of the second part. So the second part is a program OR2, and this one, it actually takes input from standard in. That's what this pipe is doing. Connect the standard out of this program to the standard in of the second program. So what this do is, this is called the maybe interactive mode of Python. So what we're doing is we're running Python, but we're not running a full Python program. We're just running one simple Python statement here, let's say. The statement is called print. So it's just we'll print out something. So for example, we print out character A. So this is ASCII, and we print out it 18 times. That's why we times 18. Then there are other things we want to print out, but those other things do not correspond to any ASCII. That's why we are directly using hex number here. So you can tell this one is actually an address, is a return address here. Then this one actually matches to this. Okay, so the 8 times 18 corresponds to the buff. The buff is 18 bytes. Then we have the actually corresponds to this part. The buff is 14 bytes. Then 4 bytes doesn't really matter. Then we have another 4 bytes, which is the address of print secret. That's how we get. That's how we put it here. Then another 4 bytes doesn't matter. That's why I put A0. You can put whatever garbage there, doesn't really matter because we're using them. Then we're putting the parameter 1, 2, 3, 4, 5, 6, 8, 0. But because this is little endian, so this is most significant bytes. This 12, hex 12 is most significant. That's why we need to put it at a higher address, and a higher address is the last one, right? So that's why we put it in this order. Does this make sense?
Yeah, I think so. Thank you.
Okay. Yeah. So let's quickly try if this works. I hope it works. I don't remember if I reboot my system. If I reboot my system, then it may not work. We need to change the return address. Let's see what we have here. We have this. Okay, if we run this, it will generate this return. This will give us the function of print secret. Is it the same? 622D. 622D. Oh, it's the same. So probably I didn't reboot. So if we just do this, we will overwrite the return address, get segment fault. That's what we know, right? So if we use this exploit, then we should be able to do exactly what we want here. We are not overwriting anything above this. We're only overwriting tier here. And after this, what we do is we will get in here, we will compare this, congratulate, then we will exit. Because of this exit, there is not supposed to be any segment fault. If without this exit, there's a return, then because the stack is not balanced, there will be another segment fault. Okay, let's try this. Okay, so this is how it works. So you need to do this as a part of your homework, but because you are using a different machine, at some point, address space layout randomization was enabled. You need to fill the address. Okay, so I hope this is clear now. So last week this part was not clear, but we want to do something more interesting than this. Okay, for example, can we return to a function with many arguments? Here we're only return to one function. So obviously this is doable, right? This is exactly the same technique we used just now. It's not that difficult because we're just overwriting more parameters here. So no matter how many parameters this function takes, we should be able to do it. So this part should be easy. And as a homework, you are going to crack one with 3 arguments. What interesting is, so I will skip the demo for this one because I think you can do it. What interesting is, can we return to a chain of functions, right? Instead of just returning to one function, can we return to a chain of functions? You know, that would be very fun, right? We can call multiple functions, chain them together, do something very complicated. Each function do something simple, then we do something complicated. Let's see if we can do this. This part is a little bit confusing. So I made several slides here, try to explain the step by step. And we probably also need to debug this, and you can see what's going on. We will do the 32-bit version first. The 62-bit version will be a little bit different because of the parameters. If we're not talking about parameters, everything will be the same. If those functions we return to take parameters, that is where things are very complicated. You can imagine you have to glue a lot of things together to achieve something useful. Okay. So let's say we are still using the function, the program we're using, like this one. Okay. But we're not calling to this print secret anymore. we're calling to functions like f1, f2, f3. Okay, many of those. So before the epilogue of the variable function, so this is what the stack look like. Okay, we have the buffer. Then there may be some paddings and by the compiler. Then there is a saved EBP. The value doesn't matter. Let's say it's 8. Then return address, we want to overwrite it to our target f1. If f1 take arguments, we can put arguments here. Doesn't really matter. Then remember that because of the vulnerability is from the string copy or gets, we only have one chance to override this whole thing. Okay, we don't get a second chance to override it. Only one chance. We have one chance to override this. So if the attack requires us to override it twice, it means it's not going to happen. We cannot do that. So after the epilogue of this vulnerable function, what happens is the ESP will point to 4 bytes above the return. That's what we saw just now. ESP will point to here. EBP will have this value A, and the EIP will point to the function f1. Then we run into the function of f1. So after the prologue of f1, what do we have? We will have EBP 4 bytes higher than previous EBP because the stack is not balanced, right? Will be 4 bytes higher. The ESP at this point doesn't really matter. It may be somewhere here. Doesn't really matter. Okay. Then we can put the return address f2 here. And after this, function f1 eventually will return. When function f1 returns, it will use this address as return address. It will jump to f2. So what we have here is after the epilogue of f1, the ESP will be even 4 bytes higher than after the epilogue of the vulnerable function. And the EBP will still be A, but it will override the bytes on the stack. And the EIP will point to f2. Then after the prologue of f2, what we have is we will have we'll have 3 A's on the stack. It's overwritten by the function, by the push EBP instruction for 3 times. And we can keep doing this. We can have other return address here. Okay. So looks like it's possible for us to call as many functions as possible, right? For example, if we want to call functions, let's say we only want to call functions without parameters. And because the stack will be moved up a little bit, 4 bytes each time, we are actually able to return to a chain of unlimited number of functions. So this is very important. Actually, the return-oriented programming, which we will discuss at the second half of the semester, is actually using the exactly same feature of the return instruction. But in that case, we're not returning to functions. We're only returning to pieces of a code. Those can be garbage, but those garbage can be interpreted as valuable, useful instructions. We're just returning to them. We do not return to full functions. Here, we're returning to full functions. So as long as you fully understand these parts, it will be much easier for you to understand the route in the future, because route can be very confusing for some people. Okay. So let's say, what do we do here? This is a part we can override from buffer to everything opposite. What we do is, this part we put garbage there, doesn't matter. The padding, we put garbage there. Save the EBP also we put garbage. Then we put the return address F1, F2, F3 here. Just those 12 bytes. Then what will happen is, first, this variable function will return. Then we will return to the function F1. After function F1 execute, it will treat this part as its return address, so it will return to function F2. Then F2 will keep returning to function f3, if you put more address here, keep returning until at some point, let's say f3 is the last function you want to return, and there is no f4, and f3 there is no exit. F3 the function also has a return instruction, and that return instruction may generate a segment fault because it's going to treat the next 4 bytes as its return value. But the next 4 bytes we never took care of it, right? The next 4 bytes, which is here, could be some garbage. It may not be valid code. So that's why eventually after function f3 returns, we will go there and generate some segment fault. So let's say this example. This is a very, I call this overflow return chain. We will do 32-bit and 64-bit. This function, let's see what we have. The main function will just print out the address of all those 5 functions. Those functions are, the first function is print out knowledge. The second one is, the third one is power, and also just the power. The fourth one is friends. The fifth one is bacon. Okay. So what we're trying to do here is we want to print out knowledge is power, friends is bacon, right? That's what we're trying to print out. If we do not print out that, this program will print out IPT the full. Right? So use the technique we just described. Let's say, I think I have all the. Oh yeah, I have it here. I actually have the. Oops. I actually have the exploit or ready. Let's say. Where are we? Overflow return chain. Okay. So I don't think the makefile has any special here. We don't have the canary, which we will talk about maybe next week. That's it. We do have the stack is not executable. We're not executing anything on the stack in this case. So you can see the main function is exactly what I showed you. We have so the goal of this one is to print out knowledge is power, friends is bacon, and those are the 4 functions. Then let's take a look. Let's craft this instead of just directly using the exploit. So the first thing we need to figure out is what is the distance between the buffer and the saved EBP, right? So we do an object down. We do see maybe this one. Okay, so you can see we have the variable function, and this is where the variable function called gets, and you can see gets is actually the parameter for it. The argument for it is the buffer address, which is EBP minus E. Okay, so which means we need number hex, number E, those kinds. Then we run this program, so it will give us this address. So we just override a little bit. It will not generate segment fault because we're not overwriting the return address, right? If we override a lot here, it obviously will generate a segment fault. That's not what we want. Okay, so we want to print out those things. Then let's do a Python. Let's use Python. Print. So we know we first need how many garbages? E, right? So this part can fill the buffer. Okay. After fill the buffer, what do we have? We have those 4 bytes of saved EBP, which we don't care. And we put another 4 bytes of garbage there. After that, we will put the address of those functions there. So how many functions we're calling? We're calling knowledge is power, Francis Bacon. So we're calling this for 6 times, right? So we copy this for, let's copy this for 6 times.
Hey, Dr. Zhao, this is Phil. I'm sorry to interrupt.
Yeah.
Did we start recording for this session?
I did. Yeah,
Okay.
it is recording. Yeah, it is recording. Yeah. So let's see what do we have here. So we want to for the first one. So it's 2D 62. Oops, use the X here. 2D 62 55 56. So this one print out what? This one print out knowledge. The second one will print out ease. So it's 4A 6 2 5 5 5 6. After that, we'll print out power, which is 6 7 6 2 5 5 5 6. Okay. Then we print out the France. Okay. 6 2. But you guys get the joke, right? Francis Bacon. Did you hear the joke before? Knowledge is power, Francis Bacon. You don't know that?
I have not.
Okay. So you can Google that later. There is a website dedicated for that joke. So you can even get a T-shirt for that. A lot of funny stuff there. So 2A 5 5 5 6. Okay. So we put 5 addresses here, or 6 addresses here. So one of the addresses, the second one, which print out is, we actually use it twice. We use it here and also use it here. That's the same one. So this is supposed to give a call return to the chain of functions here. Oh, I forgot to add this to this function. So this will override the return address on the stack and print out this. And the reason there is no segment fault is, like I said before, is because the last function here, I intentionally add an exit here. If there's no exit, this function will return. When they return, it will return to some garbage address, and it will generate a segment fault. So this is a 32-bit version of this. The 64-bit version is actually the same. So I'm not going to type this, but you need to try this by yourself and with a different address. So as you can see, there are zeros here, and because the vulnerable function here is gets, it doesn't really matter. The 0 doesn't stop it from copying things. So address here, we have a lot of zeros here. You can see the 64-bit version of this. The address is actually at the text address, the code address is at a very low address. Okay, it's a very small number here, so it will generate the same results. Okay. Any questions for this one?
Hey, Dr. Zhao, if there was either input parameters or returns assigned to the print functions, would that change the location that we would have to chain these return addresses at, or do they line up on the stack sequentially in 4 bytes even when there's params?
So the key here is we do not have parameters. When you have parameters, things change dramatically. Like I said here, we're going to discuss that. Things change dramatically. Sometimes it will make it impossible to exploit. So without that parameters, we can call unlimited number of functions. Jeremy, do you want to say hi? This is Jeremy. He somehow intruded here. Okay, Jeremy, go back to do your taekwondo. Sorry guys, he is intruded. Okay, good. So so the next one we're going to say if we can call many functions if there are parameters. You ask a very good question there. The key here is you need to understand what the core E is saying from the stack. Because as long as you jump to the core E will say the stack at a very fixed view, right? Which part is the return address, which part is the argument, which part is something else, right? For example, this is a doable thing. Let's say we can override everything from buff. Okay, we have buffer, we have padding, save the EBP. We put the function 1 here, address here, and function 1 takes one argument. And that argument is not supposed to be at this address, okay? Because of the unbalanced flag, the argument is actually 4 bytes higher than this. So this is exactly the same what we showed in the first example. In the first example, remember when we override this, this is where we override the address of print secret. And we put the parameter of this function 4 bytes higher or 8 bytes higher. So we leave this part. And this part is treated as a return address of the return after print secret. So this is where we can put another function's address. And that function will have the same view as a print secret. So it will consider this part as its parameter. Okay. But of course, here the problem is if we override this, no, we're doing this. So if we override this, there are many combinations we can do. Function 1, if it doesn't take any argument, we can we don't care about this part. If it take one argument, we have to put the argument here, which is own return address plus 8. If it takes 2 arguments, it will place here and here. In that case, we cannot put the argument for function 2 anymore, because function 2 will treat this part, arg f21, as its first argument. So they overlap, and we can only override it once. Well, there is a lot of special case. If you are smart, you really argue this. There is a special case. What if the second argument of function 1 and the first argument of function 2, they are the same value? Okay. If we carefully craft that, they are the same value. This can actually happen, right? We can make function call function 1 with 2 arguments, function 2 with 1 argument, if they have the same value, right? But if it's not the case, because that's very difficult to craft anyway. So it's very difficult. So in this case, if let's say function 1 has 1 argument, function 2 has 1 argument, what we can do is only we can call 2 functions, those 2 functions. We cannot call the third function, right? If we want to call the third function, where are we supposed to put the address of the third function? We're supposed to put it here, or put it here, right? We're supposed to put it here. But here we're putting the first argument of f1. We can only override it once. So there is no chance for us to put the address of the third function here. Of course, you can argue that if we carefully design this, the first argument of f1 could be the parameter, could be the address of f3. So they are the same value. Then in that case, it does work, right? But you can see in general, this is not a doable approach for us to call unlimited number of functions. Make sense? There are many different combinations we can do, but it's not like we can call this for unlimited number of functions. In this case, we can call 2. Does that make sense to you? I'm not sure who was asking before.
Yeah, it's Phil again. Thanks. That's perfect.
Yeah. There are some, like I said, some special cases. You carefully craft this to make sure the return address and the parameters, they are actually the same value. But they are very difficult to pull off, first of all. The second is even if you pull off that, it usually cannot do something very useful. But this is very important because this can help you understand ROP later. So ROP is basically playing things here. Okay. So next we're going to move to another a little bit different topic. And this is, we're going to do 32-bit and 64-bit of return address and the return to the share code. So this is the original buffer overflow problem. It's where you put some kind of share code under the stack, and the share code is arbitrary code you put it, and then you can execute from there. The problem is, well, after 20 or 15 years of the advancement in the defensive techniques, so those kind of share code or share coding It's extremely difficult to pull off, but they are classic problems. We have to fully understand this. So we're looking at an overflow function called overflow return 4, and this is a C code. Doesn't really matter, it's 32-bit or 64-bit, but we will compile it to 32 and 64. So the difference here is we only have two functions. One is the main function, one is the vulnerable function. The vulnerable function has a buffer which is 30 bytes, and we can overwrite that buffer because there is a vulnerable get function, and that's it. So if we run this program, it will just IPT the full. Our goal here is we want to take full control of the machine. We want to run arbitrary code on this machine that has this vulnerable function, this vulnerable program, okay? Of course, right now this program is just a local. Imagine this main function is a network function, or the get is not getting data from std in. The get is getting data from, let's say, internet, right? Then you can send some package to this program. This could be a web browser, not web server. This could be a piece of vulnerable code in a web server, and it gets the content from the internet, and it will overwrite the buffer, and you can run arbitrary code on a remote machine. So this can be a remote code execution vulnerability. Right? So what we want to do here is we want to overwrite the return address. Okay, to do that, as long as we can inject data big enough, we should be able to do that. We already say we have seen how to do that, so this is not challenging. The second part is we want to know what to overwrite. Okay. Obviously, we want to overwrite the return to some malicious code. So we need to know the address of that malicious code. After that, what malicious code we want to execute here. Okay. Obviously, we want something that gives us more control, that we can fully control this computer. So, and that is usually what we call the share code. So share code is a piece of code, usually only 20 bytes, sometimes could be bigger, 30, 40 bytes. I haven't seen something bigger than 100 bytes usually, you know. There could be with some kind of changing things here and there, we can get it big, but not too big, just most of them are just 50 bytes, something like that. And that 50 bytes can give us a shell, give us a bash, give us a, so we can type things, so we can fully control the computer. Okay. So this is what the stack look like. We know this is a buffer. Okay. The buffer may not be this size. When I draw the buffer, I mean the buffer and also the paddings. And we have the saved EBP. We have the return address. So what we want to do is we can override this part. Okay. We know we can override this part. We can override this. But what do we want to overwrite? So what we have been doing so far is we are just putting garbages in this part. We don't care what we put here. We put garbages here. What if we put malicious code here? We do not put garbage here. We put some malicious code, share code here. So what we do is, this is the part we can overwrite. So we put share code here. There will be code. Then we overwrite, we first overwrite this. So we get the share code here. Then we overwrite the return address to make it point to our share code. Then when this vulnerable function vulfoo returns, it will not return to the print secret. It will not return to F1, whatever. It will return to our share code. And our share code will give us the share. So the share code could be big, could be small. If we have enough space, let's say, we can put some knobs in front of the share code. The knob, so knob is one instruction. It's basically an instruction that does nothing. It will just skip it, go to the next instruction. So those kind of instructions are very useful for us because it will not jeopardize anything we are doing here. It will just go to the next instruction. And in this architecture, x86 and also 64, lob is 1 byte, which is perfect. If it's 2 bytes, we were worried if we jump to the middle of it, what will happen, right? So the lob is 1 byte, and it's a hex 80. So if we put a big sled in front of the share-code, it means as long as we jump to the middle of the sled, eventually it will go to our share-code. So we don't have to know the exact location of our share-code in this case. This is not required for the example I'm going to show you, but it can be very useful in some hacking challenges. Because if you can put a huge sled there, the chance for you to succeed is much higher. You only need to jump to there. You don't need to find this address, right? So we're going to use Overflow 4 62-bit version as an example. Let's take a look. Overflow return 4. Let's see what we have here. Oh, this is a one have many different versions. Which one we're supposed to use? So NX is not executable. NC is no canary. Okay, we're going to use those two, I think. Let me check my file again. Yeah, those one has no protections. Okay, yeah. So we're going to use those two. So let's start with 30. Let's take a look at this 62-bit version. We already see the source code. The problem here is the same. There is a gets function, and the gets where the vulnerability will override the buffer and everything above that. And you can see the buffer is at EBP minus 30 in hex. So even though at a C code level, we have the buffer at a C code level, the size of buffer is 40. Oh, it's 40 here. But actually the distance between its beginning to the saved EBP is 30 in hex, which is 48 bytes. So there is 8 bytes of padding added by the compiler. So the slides I have here is, oh, I think this is correct. So what we have here is a 30, right? So this is gets. So if we want to exploit this, we want to put the share code here. So we're going to talk about the share code. By the way, there are many websites showing giving you different share code. There are also tools for you to generate share code and make changes to a share code. So this is a share code we're going to use today. And the link here, you can, this is actually a very useful website. This author, he has many useful hacking tricks, all kinds of blogs. You can take a look. He talks about all kinds of advanced hacking. So this is more like an introduction to hacking class, right? So after this class, if for example, my son was, you say he was doing Taekwondo. So in Taekwondo, we have what? We have a white belt, orange belt, yellow belt, red belt, and the master is like black belt, right? So after this class, you are kind of like, you're not white belt anymore. You're like the second level, yellow belt. So this class is getting you to the yellow belt. If you really want to be the black belt, then you need to do all kinds of those things by yourself. Sometimes there is no class, right? And many of you probably heard of DEF CON. So DEF CON is like the Olympics for hacking. And some of the organizers of DEF CON are actually from a previous institute, Arizona State. So they are super good hackers, and I published many papers with them. So anyway, so go back here. So this is the share code we are going to use today. So this share code can be used at a 32-bit version computer. The share code itself is only 28 bytes. So this is the machine code of the share code, or just the hex value of the share code, and those are the instructions. So let's take a look at what these 28 bytes do here. Why it can give us a share. Okay, remember, our goal here is to getting a share. So we want to run this, we want to execute this system call, and giving the parameter being sh. So it will spawn a new, not real new process. It will change the current process into being sh, replace it with being sh, and this is a system call. So one more time on this page, the parameters we are going to give it is the EAX is value 11, then ECX we need the string address, EDX for this purpose we just put 0 because we don't need to add any environment variables. Also, we do not want to give any argument to this one, so the second argument we got 0, the third argument gave 0. So second argument is in EBX, the third argument is in EDX. The second argument, this one is in ECX, which is the address. The first argument, this one is not a real argument, it is a fixed number 11. So let's take a look what we're doing here. So the first instruction is just XOR EAX EAX. So this is exclusive OR operation on one register. The output is, the result is the EAX will just be 0. After that, we will push EAX. So at this point, we don't really care where the ESP is. We don't know where the ESP is because we start from executing here. We didn't set up the ESP, but it doesn't matter. What we know is we push 4 zeros onto the stack. Now we have 4 zeros on the stack. After that, we push 2 big numbers here. That looks a little bit weird. Why we're pushing 2 numbers? You will see later, okay? So those numbers, first of all, you need to pay attention that this is little endian. So this is high, this is low. Also, the left-hand side is low, the right hand is high on this figure. So when we push 6, 8, 7, 3, 2F, 2F onto the stack, what we actually put is this 2F is no address, right? So this 2F we put here. So there's a lot of 2F here. 7, 3 will be higher, it will be here. 62, 68 will be here. After that, we push again 2F. 2F will be here. 62 will be here. 9, 6, 9, 6E will be here. Okay. So can someone guess what this is? This is 8 bytes and ended with 0. What do you think this is? What kind of things you have in memory ended with 0? At the C level.
Strings.
Yes, exactly, strings. So if this is strings, where should we read the strings? Starting from here or starting from here? Starting from the 6.8 or from the 2F? Which is the lowest address? The lowest address actually is 2F, right? So strings is done from lowest address to high address. So this is the direction we're going. We're going 2F, 6.8, blah, 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 then get to 0. Okay. So if this is strings, then this is the value I copied here. As we can see, we have 2F, 6.2, 6.9, 6E, blah, blah, blah. So if you map this to the ASCII table, you can find out this is actually forward slash BIN, forward slash SH. So this is exactly the string. It's not exactly the string. This is the string we want here. The difference is we have 2 slashes here. Why do we have 2 slashes instead of 1?
Does one escape?
No,
No, it doesn't. It's forward slash.
Exactly. That's a very good guessing, and that's also confuse people, right? Because in C or in the only the backward slash is actually the escape, right? So you need to know that in Linux or whatever Unix-based systems, this slash, so the forward slash, or we just call it slash, it doesn't really matter how many you have. They're the same thing. See? Technically, the program you have is here, right? But if you add many slash here, the Linux system will just treat them as 1 slash. So for example, we can run, obviously if we want to run this, let's say we run a bash here, right? This is not bash, some share here. We can run it, okay? It works, right? But if you put many number of stashes here, it's the same thing, it still works, okay? Linux doesn't really care about this, okay? So that will make your job easier because you want this to be exactly 8 bytes. So you don't need to put any zeros there to make your job slightly easier. So that's why there are multiple stashes. So don't let that one confuse you, okay? So now we have this string here, and this string is pushed to stack, right? So which means right now the ESP points here. The ESP has the address of our string, which is bin sh. Then we move ESP to EBP. So now EBP points to this address, okay? Then we move EAX to ECX, and EAX is 0, so ECX will also be 0. The last one is we move EAX to EDX, so EDX is also 0. So now we set up all 3 registers here. Yeah, we need to set up 4 registers. Now we set up 3. EBX points to the address, which is a string we push down the stack. ECX is 0 because we are not giving any additional command line argument to bin sh. EDX is also 0 because we do not care about environment variables. After this, we only need to set up one more register, which is EAX. It has to be the system call number, which is B in this case, which is 11. So after this, in 32-bit version, we do this int 80. In 64-bit version, you will see later, we use a different instruction. And also in 64-bit version, the system call numbers are totally different. 11 is not executed anymore. 1 is not, 0 is not exit anymore. Yeah. So here, we will do 80. So if we execute from here, and everything is successful, what will happen? The current process, the vulnerable program, will be replaced by this shell, right? That's what is going to happen. So we're getting a shell. But the interesting thing is, why there are 3 more instructions after that? Because if this is successful, the whole address space is replaced. These 3 instructions will not be there anymore, right? There is no chance we're going to execute this. But why do we have this? Let's take a look what they're doing first, okay? The first one is we're going to XOR EAX. So EAX is 0. The others, EBP, we didn't really change it. It's still the pointer to the string we have. ECX, EDX, we didn't change. Then we increase EAX, so EAX is 1. Then we just do the system call. So it looks like this system call doesn't care about other registers, only care about EAX. So if we check the system call, this system call is actually exit because EAX is number 1. EBX is 0. Okay.
Doesn't inc add 1?
Yes, this is just an increment. This
Oh, okay,
instruction
my
is
bad,
increment.
my bad.
Yeah.
Got it.
Yeah, so this and 1. So here is 0, right? So here we're adding 1. So we're going to call the system call exit. Okay. So the question I have is, I guess I actually shared it. Why are we doing this? Why are we doing this?
When you leave the shell, you'll have that final call still, so you can exit with a code 0.
That's not true, because if you leave the shell, that will be the shell's program, right? You will never jump to here, right?
Oh, okay.
Right, because the program is totally replaced. So if you generated the shell, you will never run here.
Sure.
So the reason we have this is, what if this system call is not successful? For example, there are some system firewall or whatever to stop you from calling the system call. So that happens if you do not have anything here, then you were going to execute some garbage, right? Then the program will crash. If you are attacking someone and they are doing something, they suddenly say the program crash in a weird way, you get suspicious, right? So the purpose of this is we just want to clean up things, right? If this is not working, then we go to the next instruction, we exit gracefully, that's it. So it will not generate any segment forward, generate any dump, right? So that's a share code. So so now we know what we want to put on the stack, which is a share code. The other thing we need is the address of that share code. Because it's on the stack, it's not in .text, it's not in .data. It could be anywhere on the stack. So we need to know the address. Maybe not exact address if we have a big knob there, but if not, we need the address. And there are many ways to figure out the address. For example, if there are other vulnerable programs and the other program can have some information leakage problems, and that information leakage can disclose some information to you. Or for our class, we will just debug the program to figure it out. Or if you are not able to debug the program, you are not able to find out some information leakage, there is always other way you can try is brute force. You just guess. You can write a script to automatically guess this for thousands of times, and you only need one time to be successful to crack the system, right? So actually, we're saying a lot of hacking we're doing involves guessing because there are randomness there for protection, and we have to guess. There's no guarantee it will be successful. Okay, so there is another. Did I put it wrong? So it should be overflow 4. Okay, I probably put it wrong. So for today's class, there is another thing is we're going to use GDB to get the address of where we should put the share code, which is the address of the buffer. But there is another thing is when you use GDB to debug something, GDB will add some environment variables there. It will push something onto the stack. So that's why if you, let's say, if we run this program, we have we run this program, or if we use GDB to debug this program, they will have a different stack layout. There will be, I have seen something like 100 bytes off. So because of the 100 bytes off, what you can do is have a big knob there and give you more chance. Or today we're using another technique. So there is a script I find online. So it will be in this folder. You can use it later. So this is a script is the RSH. This script, what this script does, it will make sure no matter you are running a program or you are running a program in GDB, you will get the same address for it. So you will get the same stack layout. So this is how you are going to do this. First of all, disable address space layout randomization. Then when you do GDB, you need to use this script to start GDB, then debug the program. When you run this program, don't run it directly. You run it like use this script, then this program. If you want to send some standard message to this program, you can still use a pipe to do this. It's the same, but always use the script first. So this will balance, will make the stack consistent, no matter you are using GDB or not. So we're going to try several ways to crack this. Okay, let's say the first one is we're going to put the share code here. So this is our buffer. We checked that it's 48 bytes, right? 48 bytes there. We're going to put 20 bytes of knobs here. Then another 28 bytes of the share code, which is what we have there. Then we have then we are going to this save the EBP part. We just put A0 dot matter. Then we are going to get this address return. Then so we are going to overwrite this whole part, which is 48 plus 8. We're going to overwrite 49 bytes to say if we can get a shell. Okay. Let me. This is a share code part. I will copy that share code part. Okay. Let's get the address first. So remember, we need to use this one. Then we do GDB. We'll do OR4. This is a 32-bit version. So what do we have? We have the vulgar function, Overflow, right? By the way, when we do this, I don't have the plugin installed there, so it's a little bit harder to read this, but we don't have. Okay, so we can run this. Now we are in the vulnerable function. So we are going to set a breakpoint somewhere. We want to get the address. We want to know what is EBP minus 30, right? So it will put the EDP. So we can put a breakpoint here. So we can create a breakpoint. I think we can do root fun plus. So this is what, 27? 27 is 20. Is this hex or decimal? I don't know. That's just, oh yeah, it's decimal. So we do this, then we do save, which is continue. We're hit our breakpoint. Now we are at that address. See, so this is a PC points to here. So EDX right now has the value we want. We can do a print EDX. Oops, we need to print hex. So EDX, obviously this is a stack address, right? This is where the buffer is. So what we're going to overwrite is, let's say, how do I do this? I don't have a notebook or anything. Just, my browser is not working. Okay. Let's just, okay. Maybe look at a minute. Let's try to craft the exploit. So we said that we want 20 bytes of lobs, right? So 20 bytes of lobs, which is hex 90, when we want 20 bytes of it. After that, we want the share code. Let me copy this address here first. Then I guess this is a share code. Let me copy this. I hope there's no strange characters when I copy this. Otherwise, it will be very painful. What do we get here? Oh, that's a new 90. So where did we copy? 28. So we're going to EC. Okay. So that's the share code part. After share code, what do we have? We have save the EBP, which is just garbage. Put A here. Then we have this return address. So this address, you can see we're doing 32-bit. This is at the beginning of this is top of the stack, top of the memory space. So it starts with OF. So that's the stack. So here we put F8, FC, FF, FF. Okay, looks like that's right. Let's say print. Let's see if there's any syntax errors. Okay, looks good. So this one is gets, or this one gets. Yeah, we can use. Copy this one. Copy this. Oop. We have this one here. So we run this one again using this script. $sign. Okay. So this command will use Python to generate some exploit. Oh, sorry. didn't finish this part. Is that correct? I think that's correct. So this will generate this exploit and send that exploit to stdin to this program, and we're going to run this program again from the beginning. So now we are in function full. I think we have a lot of breakpoints, so we just continue. So now we are here. So we executed once. Now we are in move. We're not calling, so we do it once more. So now we're about to call this. Now we call this one. After we call this one, technically we already overwrite the stack. Let's take a look at the stack. So where the stack is, we can print out EBP. Where's the EBP? This one. So we examine here. See, you can see those 4 8s, and the EBP minus 30, right? Hex 30. So EBP minus hex 30 is where our buffer is, and you can see it's 1990. How many bytes we put there in total? 48 something? 46, yeah. Let's say 46. Hey, how do I do bytes? Wait, B? Oh, yeah, B. Okay. So this is what we overwrite there. Let's check if that's correct, right? At the beginning, we have 20 bytes of knobs. That's 20 bytes of knobs, 90. Oh, from here actually. Then after that, we have the share code starting from 31 to somewhere here, right? Because this 80 is that int. There are 2 int 80s, right? That's 2 system calls. So from here to here, starting from 31 to 80. Let's take a quick look if that's correct. Where is our share code? 31 to 80. Then after that, we have saved EBP, which is 4 bytes. Don't really matter. Then we have the return address, which is FF, F8, which is here. Ooh, I put it wrong. It's CF. It's CF, not FC. Okay, we need to redo it. Where's our? So this is CF. Yeah, that's right. So we do it again. Continue. We do once. Just a bunch of this. Oh, we didn't call it. Now we call it. Now we examine it again. So we have CF, F8, which points to here. Okay. We don't note that we don't have to point to here. Technically, the only place we have to point to is here. So we can point to anywhere here just to increase our chances because we have 20 bytes of stuff. So we're going to get it to return. So we're going to execute another 5 instructions. So we're at 8 with it. Okay, now we are at return. Now we're at return. So at this point, ESP is supposed to point to what? The return address. Let's say if dollar. See, the ESP right now points to our return address, say FF8. The return is going to pop that into EIP. Right? So if we say the value of EIP, the value of EIP right now points to variable function 26. Oh, yeah, because we're going to do the return. So we execute one instruction here. You can see now we are in our share code. Now, if you do P EIP, we're in our share code. We're at this address. GDB doesn't really know the prototype of this function because there's no symbol there. We just jumped to there. There's no symbol. It's not like the Overflow or whatever. They may have symbol there. Then we cannot do a disassemble here because this is not a real function. From GDB's point of view, it's not a real function. but we can still disassemble it using X. Then we can do disassemble it. So I here means we disassemble this as an instruction. So let's say we disassemble 40 instructions, starting from the address EIP. Okay. So what do we have? We have the knob, 20 knobs at the beginning. Then we have the exact code. We have the exact code here. EAX, push those, and it actually ends at here. After that, there is some garbage. We don't really care. We didn't put it there. It's just some garbage on the stack. Why do we put it from here to here? Okay. So we just keep doing, right? We just run this. We just do continue. Oops. See, even though there's error, but you can see the process, this one is executing a new program, dash. So this is how we actually get what we want, okay? If we don't do GDB, let me get the shellcode there. This is the correct one, because each time the address could be slightly different. So the one I have on the slides is not working right now, but you can understand the syntax here, right? So we're putting 20 bytes of knobs, the shellcode, 4 bytes save the EBP, the return address. So if we want to run this directly, we can do is so we can do a Python this. So this will generate the shellcode. Then we'll do sh. Then we will do OR4. This is not enough. We need to do a cat there. So when you do this, remember you need to do a cat. Otherwise, it will return directly. So the cat will open a file, an STD there, to make sure this program will keep listening to your command. So this is just a trick you need to remember. So let's do this. We put them together. Where are we? We're here. So after print out those exploit, we do a cat here. Then we run this. Remember, you also need this to make sure they're at the same stack location. So now we get a shell. We actually have a shell here. You can see it's waiting for my input. So I can do who am I? It says that. I can do a ls. It's our current folder.
Sorry, I missed the part. What does RSH does?
Oh, so let me explain this one. To return to the exact location on the stack, what we need is we need to debug the program. In this example, we debug the program to find out that buffer is on the stack, right? However, when we debug that, we use a tool GDB. GDB will change the stack layout from the original program. So it will have a different stack layout from the original program. So even if you get the address from GDB, that address may not be the same address if you just run the program. Okay. So this script r.sh will automatically make things consistent. No matter you are using GDB or directly run the program, they make sure they have the same stack layout. That's why when you do GDB, you need to use this. When you run this program, you also need to use this. Okay.
Well, yeah. So one question is, so I guess in this case, oh, so this makes it consistent as GDB, so it makes the stack of this regular program just like GDB.
The stack layout is just like run it with GDB. Yes.
Yeah, just like GDB changes it a little, this program changes it by a little too. The same.
Exactly.
So how does it know by how much GDB changes it, and how does it apply it?
Okay. I didn't really check how this script works. You can figure that out by yourself. You just check how it works. Yeah. this is not the only way. I mean, even without this, you get a rough address. You maybe uh, because you know GDB is put something on the stack. So the address without GDB is always a little bit higher, right? So you can get the address from GDB, then change the address, make it higher, and keep guessing. Eventually you will hit it. But that's why the log here comes very handy, because the log here, the 20 bytes give you uh, some room for you to have errors. That's basically room of errors here, right? So here we can see this is actually a share, right? We can do anything here. Yeah, this is a share. We can exit, quit, then we come back here. But like I said, because we have a log here, we do not need the exact location, the exact address. Remember, this address we are giving here is pointing to here. We don't need the address. We can point it to somewhere here, which is 10 bytes higher. It still should work. So for example, this one is a F8, and we can change it to F8. Okay, it still should work because it still hit the log, right? So it still works. Or we can be even higher. After A, we can have A1, right? Still should work. Oops, that's too much. Is this still working? Okay, maybe A1 is too much. Oh yeah, A1 is too much. After F, we should have something like this one should be right now is CF, so it will be D0, right? D0 and 0, 0. This one may work. Yeah, this one work. So if we change to A1, that's too much. We probably jump to the middle of the share code, or we jump to here. So it doesn't work. Make sense? By the way, there are some errors in my slides here. They should be OR4, not OR3. Also, this should be 4. I will change that. Okay. So this is your first share code. We put it on stack. So there is another way to do this. There are many ways to do this. Remember, we can overwrite from here to everything above that. What if this place is too small, let's say? Let's say we're putting the share code in the buffer. What if the buffer is only 6 bytes? What if it's too small that we cannot fit in the share code there? So this is very simple. We can put the share code on top of this. And the advantage of this is when we put it here, even here we have 48 bytes, we only have 20 bytes of logs. But if we put it here, we can have a huge log. We can have a 1,000 byte log. So increase our chance a lot, right? And here we just put garbage because we're not going to jump here. We put the buffer garbage there, then we put the return address pointed to here after this. Then we do this. Okay. Does everyone understand the principle here, the theory here? It should be simple, right? Let's try one without that script to see if we can make this work. Okay.
Hey, Dr. Zhao, real quick.
Yeah.
Is it fundamentally, or at least, I guess, practical to maybe make a NOP sled that's so big that you could almost, you'd have a chance at catching it even if you did randomize addresses, or would it segment out before you get large?
With randomized address, it will be tricky because the entropy sometimes is very, very high. If the entropy is very high there, the NOP there sometimes doesn't really help you a lot. But with other, for example, if you are solving the GDB problem because you are pushing hundreds of bytes or several bytes there, then the big log help a lot. Yeah. And there are other cases for old machines. You cannot even GDB it. You cannot debug. For example, you attack a remote server. You cannot debug it. So you just do whatever to increase your chance. Yeah. For this one, for the second one, let's see which one is it. We this time let's try without that script to keep the stack balance. Then we GDB this program. We are going to put a breakpoint here. We run this. Then we are, what do we want to get here? We want to get the address after return, right? So actually, we don't need the buffer's address. We still need the buffer's address. It's the same thing actually. So let's see, we just run several instructions here. Yeah, so we just get off the buffer's address, EBP minus 30, right? That's what we want. Yeah. So the address we have is CFB8. That's the buffer's address. But remember, this is inside GDB. So we exit this. Okay. Good. So we are going to craft a new shellcode without using this one. But this one, let's say, the address we're jumping to, we will figure it out later. Let's say this one, we need a 48 bytes of garbage there. We just put 48 bytes of garbage to 48 bytes of garbage to totally cover this part. This part is also garbage, so we need 52 bytes of garbage. Then we put the return address here. So this is where we put return address. We don't know the value yet. Then we put the shellcode here, so we can remove this part. Or this part we can remove. This part we can remove. So the shellcode is 28 bytes, but now we don't have the space limit. We can put as many sled as big as we want. Let's try something big. Let's try 200 bytes. Okay. Then the address, we don't know the exact address. We just guess some place. For example, here we have B8 CF FF. Okay. Let's just try if it works. Oh, it works. Is it? No. Okay. So see here, illegal instructions. What does that mean? We somehow jumped into some place. We jumped to that something in the middle, and give us maybe it's the middle of the shellcode, right? So maybe we should move the address a little bit lower. Looks like we jumped into the middle of the shellcode. So to increase the chance, we make the set even higher. Then we put this one lower. Let's put the C0. That's why. No. Okay. But you get the idea. Yeah.
After 52 bytes, it's the return address, right?
Yes, this is a return address.
Yeah, so it shouldn't it be the address pointing to the no-op operations?
Yes, but we don't know exactly where it is, right? We're trying to figure out where it is. So hold on. That one is what we get from GDB. So it should be higher than this address because GDB address will be lower. So address we get from GDB is somewhere here. Should be higher than this. Okay, we should be adding things, not. So for example, CF. What is higher than CF? D0. Let's do D0. Oops, what's wrong? I missed something. Oh, sorry. D0. I did a DO0. Okay. That's should be D0. Who am I? Okay, still get second and fourth. Let's make it. So let's say D. So each time we change this is like 200 bytes actually, right? Let's make this set even bigger. Okay, now it works. now I have a super big sled, right? I have a sled bigger than 1 MB. Then I change this one to one. So when I change to one, I'm actually changing because this is a least significant byte. I'm actually changing 100 in hex. That's what 100 in hex is what 256 bytes. I'm not sure. Okay. So, but you get the idea, right? I'm making a super big sled. Let's see if we can make the sled smaller and then the same address if it works. Still jump into the middle of the sled. Oh, it still works. So even 500 bytes sled works. Maybe 100 bytes may not work. Oop, even 100 works. We find the, did we jump to the perfect location for it? That's weird. Okay, so if the sled is 10 bytes, it doesn't work, but it's 100 bytes, it works. So in this case, we didn't really find out where exactly we need to jump to, right? We have a rough idea where we can jump to. Then we just jump to it, and somehow it hit the knob, and the knob bring us to the share code and give us the share. So the key here is for some old systems, if you do some remote exploiting, there is no way you can find out because you cannot debug that machine. There's no way you can find out the exact location. That's why you add some unusual tricks like this to increase your chance of success. Okay, let's keep moving to the next one. So now let's move to the 64-bit version of the same program, and we want to do the same thing. Obviously, the things we need to change here is first, we need a 64-bit version of share and also we still need the address of the share code at runtime. And remember that the calling conventions are different. Now we are using the registers to pass parameters, and this is a 64-bit version of this. I actually disassembled this. You can see the buffer size. I think it should be the same. It's actually, let's do an object dump here for the or64 version. It's actually the same address. It's the RBP -30. By the way, in this folder, I will share this folder with you later. You can see there are many different combinations. You don't need to work on others right now. For example, the one we're working, we disable the canary, we enable the stack execution, the 64 version, the same thing. This one is NX means not executable, means the stack is not executable. So it has all those protections there. This one is not executable, but no canary. So I disable canary there. You don't need to know what these are at this moment, but I don't want to confuse you. Those four, you don't need to work on them at every point. Okay, so where are we? We are doing object dump there. So you can see this one is at the same address. No, not this one. So we're doing gets. So this one we get the same address, RBP -30. Then this one is put into RDI. Okay, so it's basically the same thing, but there is another trick we need to use. Okay, so the distance between buffer and the saved RBP, 48 bytes. The size of saved EBP, 8 bytes. The size of return address, 8 bytes. Then this is the 64-bit version of share-code we're going to use. I tried to download some, it's not working, then I decided to use this one. So we will compile this one from, we will compile the share-code by ourselves. And this is the command we're going to use. So I have the share-code source code here. You can see the source code is this. doing this? Okay. So you will program something like this a little bit in the share coding classes. So we have this is assembly code. This is assembly code. We define there is a global function underscore start, and the underscore start we're using Intel syntax here, and there is no prefix, so we're not going to have those prologue or whatever. So what we're doing is we move. So this syntax, the destination is the first one. So 58 to RAX. Then that's because the system core number is different in 64-bit version. So as you can see, this is a 64-bit Linux system core. I don't really have the, but 11 is not executed anymore. Executed is 59. So that's something you need to be careful. Then we know the effective address of this string. We define a string at the end of this share-code. This is a share-code, only 5, 6 instructions. Then at the end of it, this is a string being sh. Then we get the RIP plus this one node here to RDI. Then we move 0 to RSI, 0 to RDX. So we get the, so we are setting up the system call registers. Also, you can see the 64-bit version of the registers. We're using different ones. The system call number, we're still using RAX, but the first argument, we're using RDI, RSI, RDX. The 32 version, you remember, we're using ECX, EBX, EDX, so it's different. And the system call instruction is not int 80 anymore, it's just the system call. So this is how we get the, we program the share code. So it is here, this is this, okay? So we can compare this, okay? There are many ways we can compare this. We can just do GCC share code, right? Then let's say, let's just do share code.elf. Okay. So when we do this, it will tell us this function has no main function. Okay. So this is like a C program or somebody, you're supposed to have a main function. But however, this one, we didn't define the main function. That's why the compiler gave us an error. So what we do is we give it some flags. For example, first one, we don't want the std libraries, okay? And everything is static. Then we compile it this way, it will give us the L file. So we have the sharecode L file, which is quite small, but this is still an L file. If we use the read elf, we can say it has many sections, right? It has all the sections, symbols. This is an L file, which means we can directly run it. If we run this will just the core system call execute bin sh. So if we just run this, it will just give us a shell. That's it, right? So, but what we need is not the full L file, right? Because this is big. This is a full L file. You can see this is a whole L file. This is big. What we really need from this? So this is a magic code. Magic number for L file is 7F elf. That's always there. Magic number elf. What we really need of this is we only need those instructions. We only need those instructions. We don't need this. So what we do is we can do another object copy. It will copy. This is one of the object file tools I mentioned in the first class. So we can dump a section. So when we are going to dump the .txt section, we only care about txt section. So let's do share code raw. Okay. Then dump this from the sharecode.l file. So now we should have a sharecode raw file here, which is this one. And this one is only 38 bytes. We'll do an XXD here, you can see. this is only 68 bytes, and this is our shellcode. So the first, those parts are our code, and the end of it is the string. That's it. So what we want to do, did we get the address for that? We also need to get the address. So 64 version. Let's try this. We do GDB. We do the 64 version of this program. We try to, what is that? Full. Right. Then we're going to run this. So we are here. Let's say, go right here. So we are trying to get the address of the buffer. So we're going to execute to where? 79. 79. Now we are here. So we just get the address of the buffer. So we just print out RBP minus hex 30. Now we get the address of the buffer. So this is the address of the buffer. That's all we need. Okay. That's the address of buffer. Then we're going to craft the shellcode. So using the command here. So we already have the shellcode ready. So what we can do is we do a cat. Yeah, we need to run multiple. We do cat shellcode.raw. So basically, this will give us the shellcode there. Right? This is a shellcode. So we're going to do this. We're going to Python. We're using the first approach, by the way. We're putting the shellcode in the buffer in this case. We have 18 bytes because this shellcode is. Hey, hold on. Which one I'm using? Because this is the shellcode is 38 bytes. Oh yeah, 38 bytes. Then we have another 10 bytes. Why we are 18 here? First of all, shellcode is 38 bytes. The buffer is 48 bytes. So we put another 10 bytes of garbage there. We're not putting any knob there. Then another 8 bytes is the saved EBP because this is 64 version. Then this one is the return address, right? So this one times 18 plus the address we just get from this one. So which is 40 DE FF FF. Then how many FFs are there? So FF it should be 1, 2, 3. Should be 3. Then 7F. Then 0, 0. Is that 8 bytes? 1, 2, 3, 4. Yeah, that 8 bytes. So this is our, okay, and we call this exploit. Now we have the exploit. If we just camp this, you can see that's our exploit. There's some A's in the middle. Then we run this again. No, sorry, only GDB again. Cat exploit. Then we need another cat to make it work. Because then we pipe this into this board 464, and it should give us the shell. Yep, it works. So this is a 64-bit version. It's actually this almost the same as a 62-bit version, but instead of just grabbing a shellcode online, we retrieve, I showed you how to compile your own shellcode, and you can either test or debug your own shellcode, and this can exploit this. So We use the same technique. We put the first technique. We put the share code in the buffer. You can do the same thing. You can put the share code above the return address and jump there. And you can put a huge knob there, so you don't have to use the r.sh script to make the stack consistent. Okay, any questions here? Everything makes sense?
Just to follow up on generating the 64-bit shell code. Is there an intuitive way to take advantage of trying to use GCC to maybe just drop off a .s file that you can get those instructions from, or is that just too convoluted? Much like it was when we tried to just look at the hex dump.
I don't understand your question there actually.
Oh, so we went through a series of steps to get the 64-bit shell code that was unique.
Okay.
I know that.
Okay.
So
So for example, you're asking, can we just omit this step? Is there any parameter we can give to GCC and directly generate something like that?
Right, because I mean, a .s file will give us machine instructions, but it might not match what we need. I was just kind of curious.
So the .sh is not really the machine code, right? So this is actually text, right?
Right.
The .sh is the text. You still compile it into machine code. But the problem is the GCC will not directly give you. That's why the GCC suites have other tools like object copy to help you. The GCC will not directly give you, let's say, generate only the machine code. It will not do that. You have to use tools like object copy to do that. Yeah.
Okay, great, thanks.
Yeah. Okay, so next, I actually want you guys to do an in-class exercise. So the one we're going to work on, some of you actually did this because some of you actually had my hacking sessions before. The exercise we're going to do is something called over the wire behemoths. So this is a 62-bit machine you can play with, and I will show you. So here I have all the instructions you need to log into that remote war game, and we can hack this together. So first, let me show you this website. So this is one of the classic war game website called Over the Wire. It has many different war games, starting from easy ones to harder ones. For example, the easy ones are like Bandit. They're technically not really hacking, just teaching you how to use Linux. And starting from the second one, I think there are some hacking involved. Some of them, for example, this one, Krypton, from the name, you can guess it's somehow related to crypto. And today we're going to do this is a behemoth, and this one has several buffer overflow challenges. And I will log in first to show you how everything works here. So you can open a terminal, then you can just type this to log in this website. So basically we are SSH in this server using the account behemoth level 1, and the password I also gave you there, AESEBOOPIF. Okay, so now we logged into this server. So we can look around what we have here. So we are at let's say we can go to the root. So now we're at the root. The root, you can see there are two important folders for us. The first one is the behemoth folder. So this is where the vulnerable programs are. If you go here, you check, then you see there are 7 levels of programs. And all of those programs are red. Remember what I read, they are set UID programs. For example, this program the name is behemoth 0, and the owner is behemoth 1. But it's a group, it's behemoth 0, which means behemoth 0, if you log in as behemoth 0, you can run this program. And when you run this program, the program's effective UID is behemoth 1. The purpose of this is this program is vulnerable. And there is a password associated with each user, which is stored in etc behemoth password, I believe. Yeah, etc behemoth password. So right now I'm logging as behemoth 1, right? So if I want to catch the level 0's password, it will say permission denied. If I access level 1's password, I get the password, which is a password I use to log in. If I get the second, if I want to catch the second level's password, also permission denied. However, the program I can play with is behemoth 1. This one has an effective user ID. When it runs, it has an effective user ID as behemoth number 2. So if I can crack this one, if it can return me a shell, I should be able to catch this. When I do this shell here, when I do this, the effective UID is still behemoth 1. But if I run this program and hack it, the effective ID will be behemoth 2, and I should be able to access it, and I should be able to catch the password. Then I get the password of level 2, then I can log into level 2, I can run this program, and I can try to crack this program and get the password for behemoth level 3. So this is the idea of this, how this challenge is designed. You can do this level by level, and to practice. So I will give you several minutes to log in here first, and then let's study this together to see what kind of problem it has. The biggest problem of online teaching is I cannot go to the classroom to see what you guys are doing. So the plan was to, I can walk to your desk so I can say what you are doing. I can help you there, get a fitting. But with this online teaching, this is really, really challenging. So, and also you cannot share screen with me because there is only one guy can share the screen. Just log in there and tell me what's going on. If you find out this folder, you find out the UID programs. So here is the password. You need to type that.
Wait, so I thought that user behemoth 1 needs to crack behemoth 0 user? Behemoth 0? No? Okay.
No. So behemoth 0 is supposed to crack behemoth 0, but this program, the effective UID were behemoth 1. That's why you can get the behemoth 1's password. If it works, yeah.
But we're in the behemoth 1, so shouldn't we break behemoth 1, not behemoth 2?
Yeah, we can only do that one. Actually, if you run behemoth 0, you can, let's say, if you run behemoth 2, you cannot even run it. Behemoth 1, you can run it.
Yeah, but the slides say run behemoth 2. That's why I was just a little confused.
Oh, your goal is to get the password of the user behemoth 2.
Oh, okay, sorry, yeah, my bad.
By running the binary of behemoth 1. Yeah.
Okay, got it.
Yeah.
And where are the passwords stored again?
It's here. It's on the screen.
No, sorry, the directory with the passwords.
It's under etc behemoth password.
Okay, thank you.
Yeah. I guess not everyone can finish this, but this will be part of the homework. So Have you logged in?
Yes, right now.
Okay.
We're expected to use the GDB on their machine, right?
Yeah, there will be GDB there. So
Okay.
usually what you do here is you do a file here, right, to understand what's going on. So this one is a 32-bit setuid L file, and remember all the tools we started before, like L trees. You can try those to get a feeling what this program is doing. And also you can do S trees. And besides GDB, there is also object dump there available, so you can read the code. Anyone has trouble logging in there? So we can see there is a main function, and the main function called gets. That's suspicious. Looks like there is a buffer overflow because there is gets. And besides the main function, we do not really find any function interesting. It's not like there's a full function. It looks like the valuable function is a main function. By the way, the hint I gave you here, this is a buffer overflow. You need to exploit the buffer overflow. I can tell you that. So there is a print, then there is gets, and gets, obviously there is a buffer, which is EBP minus 43. Then after that, it puts something. Okay. So if we do an S trace here, okay, so the print will do, basically will do the system call write. It will write password. It will ask you for the password. Then it will read some password from you. Then you read it. Then it will do another print, puts authentication failed, and also sorry. Yeah, that's it. But it doesn't mean for this one you need to, for this one, you don't need to get the right password because this is different from our homework. The goal for you is to get a shell, so you can get the next user level's password. So you get a shell, then you can do a can't to get the next level user's password. If you do, it's not like guessing the password inside this program. Yeah. The share code you are going to use, you can use the one we used before. Ooh. So first of all, does everyone logged in? Is everyone logged in?
Yeah, doing it right now.
Okay. So anyone has any issue logging in there? Okay. If no one says anything, I assume you're all logged in. So the share code we are using, it will be this one. I will upload it. So let me upload this to the chat maybe. It's not showing. I will just, it's right before I give up. Okay, this is a share code. Who are using? This share code is 8 bytes. Oop. You need to delete a new line there. This is 28 bytes share code.
One more question.
Sure.
Can we, is this like, I guess, exploitable directly from GDB, or do we need to, like, if we find, let's say, return address, do we need to run it outside of GDB or inside of? Yeah.
That's a good question. I think you need to run that outside of GDB. I think GDB cannot debug setUID programs.
Okay.
I'm not 100% sure, but I think you need to run that outside GDB. Yeah.
Okay. Okay. Thank you.
So let's calculate the address here first. So this is 43 hex. What is 43 hex? 40 is 64, so this is like 67 something. That's a weird number. Do we all get the same thing? I think so. That's a binary. That should be the same thing. Yeah. 43 hex. Yeah, that's 67. So get 67 here. So the distance between the buffer and the saved EBP is actually 67 bytes. The share code we have is 28 bytes, which means 28 bytes.
Sorry, I had a quick question. Another quick question.
Mm-hmm.
So, can we use like echo? When you do echo, does it put the byte? Can you forward the byte code using the pipe?
Oh, you do echo? Yeah.
Okay.
Yes, but not bytecode.
As in, if I do echo and then I do Python.
Oh, in that case, you don't need to do echo. You just do Python. Yeah. You just do Python.
Oh, okay. Okay.
Yeah.
Thank you.
You don't have to use echo. Yeah. So we have 28 bytes of share code. We have the buffer is 67 bytes, which means if we want to put the share code in the buffer, we can have another 39 bytes of nops, right? 39 plus 27, that's 67. Yeah, we can put 39 bytes of nops here. Then we need to get the address of the buffer. To get the address of buffer, we can use GDB to do that. In case that doesn't give us the exact location, we probably need to, we know without GDB, the address will be higher, so we can try multiple times. How about this? We still have 25 minutes. Does someone want to share his screen to lead this one? So it will be more interactive this way, I guess.
Yeah, I could share my screen.
Yeah. Okay, so who is talking?
Ibek.
Ibek, okay. Let me stop sharing the make you the Ibek. Okay, you are a co-host now, so you can share your screen. Thank you for doing this. This is fun.
Yep. You should be able to see my screen.
Yes, we see your screen. Yeah.
Oh, I kind of to this point I found that 70 is where the EBP ends.
Okay. So we actually So 70. Yeah, it's actually I did an object dump there. It's actually 67. So if you do 68, you should overwrite. Try 68. if you try 68, you should get a second for inventory.
No, I only get at 71, so 70
Okay.
is good.
Okay.
Unless I'm hitting maybe a text somehow.
Oh, right. Okay, let me think. Is it because? No, not because of that. Yeah, I don't know. Yeah.
Yeah, so yeah, I guess I can make it bigger. Yeah, so where can I find where can I find the shellcode? Oh, you posted it in the chat, right?
Yeah, I posted it on the chat. Yeah.
Okay. I don't think you posted it in the chat.
Ready? Okay. Let me. Sorry, I post to Phil.
Oh.
I didn't post to everyone. So, okay. Then give me a chance to fix the new line problem there. Yeah, I just posted. I also am going to post it on the Slack channel, I guess. Slack channel. Also, I can send you guys the website. You can directly copy from the website. If you copy from the website, you actually need to fix the new line there.
So
okay, so you find let's see, where are you? You are.
I just got the EBP here.
Okay. So EBP, that's a safety EBP address. That's not
Yes.
the.
It's after I did next instruction a couple of times, so it's like this. Yeah, so it's like at when it's push at this instruction, this is the EBP.
So that plus 8, oh yeah, that address doesn't matter that much, right? What you need is let's say the best you want is the EBP minus 43. You want that
Yes.
address because
Yes.
that's the address of the buffer, right? I mean, of course, if you get the address of EBP, you can get that manually. You can calculate. Yeah.
So I guess I could then we can do.
Yep, you can run several lines of code. Yep.
And we do.
You just
minus,
do EBP minus 43 because you can see, yeah, yep. 43, hex 43, OX 43, 0x43. Yeah. Yep. So that is the exact location for your buffer.
Yes.
So that's where you can put your knobs. Right?
Yep. So the shellcode size, oh, it doesn't really matter. So
shellcode is 28.
Okay. So we can have probably let's do right 0x90 just for now.
Yeah. It's x90, not 0. You don't need to put 0 there.
Oh, /x, yes.
Yeah. Yeah, /x, yeah. So it's 43 is sorry, 40. Yeah, 43 is actually 43 in hex is actually 76 in decimal. So it's 67 minus 28, which is 39. So you can have 39 bytes of knobs.
Okay.
Yep. Then you can put the share code there.
1 second.
Yep. So now you are not overwriting. Now you are starting to overwrite EPAP. You can put 4 garbage there, 4 bytes of garbage. Don't really matter.
Oh wait, 28 plus 39, right? It's 67.
Yep.
So we have what,
Yep.
three bytes for nothing.
4 bytes for nothing. You need
Oh.
another 4 bytes for the EBP, which is
Oh
nothing.
yeah, okay.
All right. Yeah.
So I could do just, let's say, A times, let's say, wait, how many? 4? No,
4. Yeah.
okay, all right. And then we need,
The address. Yeah. You can, yeah. Try to put that address there first to see what happened. Wrong order. Yeah.
that's correct.
Yep.
Okay.
That's correct.
Okay.
Let's just try. Second and fourth. Okay.
Yes, we
So
need diff maybe plus, is it
let's-
plus 10, minus 10?
yeah, let's think, because the address you get is from GDB, right? So GDB will push things there, so you should adding things here, make it a bit larger. Yeah.
Let's do, for instance, plus 5, or I don't know. What's the good? Maybe
Think,
we have.
think. What is a good number here?
Let's do plus 20, just because we have some. I get. Wait.
Yeah,
Plus?
because you have some lobs, right? Your
Yeah.
lobs is like almost 40 bytes. So if you add something like 30, it will be very safe. You feel here, right?
I did 20 for now, but yeah, I
Yeah.
will.
Yeah.
I'll try also minus after. So. Yeah, 695. I guess I also try. That minus 40. Oh, no, that's.
It should be plus, but you can try. It should be plus because EDP will push things there. Without running EDP, it should be always higher, right? Make sense?
Okay.
Yeah.
Oops.
How about you just try, for example, 95, after 95, you try A5. After A5, you try B5. That would be make sense easier, right?
Right here, as in D. Oh, wait, D.
That's too much. That's too much. The last one, yeah. You have 95, then try, what's the 95 a little bit higher? It's like A5, yeah, something like that. Okay, then try B5. Looks like it's too much.
Yeah, this seems.
The address I have is actually in that range, so I'm not sure. Maybe your machine will be a little bit different, or
It's not on my machine. Well, let's see. Maybe I have a feeling that plus A4 times 4 might be wrong, because we have. So at 70, right? 70 is the correct range. 39 plus.
No, it's a 67.
No. We just checked on my machine, right? 70 was the one that failed.
Oh, that matter. There are many reasons why it fails there. Actually, you need to check the binary code. We check the binary code. The distance between buffer and the saved EBP is actually 67. That doesn't change.
71 is there because he's overwriting the old EBP. That's what he was getting 71.
Oh, okay.
Oh yeah, so that's correct. Yeah.
Wait, okay, but still, it's not 4. It should be 3 right here.
Should be 4. Still be 40. 40.
Okay, look. So 39 NOPs, right?
Yes.
I'm gonna 39 plus 28 bytecode.
Yes.
Why do I have a space here? Okay.
Oh yeah, that may be the problem.
That might have been the problem.
Space might be the problem. Yeah.
Okay. Let's do B. A. 9A illegal construction. Ooh,
You hit it. Yeah, you hit it somewhere. Try a little bit somewhere nearby. Yeah.
I think maybe let's do. Nope.
Too
Yeah,
much?
90. Let's do 9.
Maybe try 0. Oh, not 0. Yeah. So it should be A. Try maybe A0.
A is illegal instruction.
Maybe try A0.
A0.
Yeah. Oh.
It must be landing somewhere over here, right? Because illegal instruction.
Yeah, looks like somewhere there. Looks like jumped into the
Ah.
middle of something, but it could also, yeah, it's more likely to jump into the middle of share code to have the illegal instruction. So that 9A is close. So since it's jumping to the
Can you again explain to me? I still don't understand. I have
okay.
39 bytes no up.
Yes.
Then I have 28.
Yes.
Correct?
That's 67 in total.
Yep.
Yeah.
Plus 4 A's. It will
save the EBP. Yeah.
But it's 71 bytes. It overwrites the 71th byte. It overwrites one extra.
No extra. No. The 70 you get by testing is not the accurate one. 70 is not accurate one. You get it by testing. The accurate one is actually 71. Yeah, because we checked the binary code. You can do an object dump to get that. So what you're doing here is actually correct. There is no 1 byte off. Yeah.
Okay.
Something wrong. Hold on. Something wrong with the share code. Oh no, it's correct. Yeah.
So again, 70 doesn't do segment fault.
Yes, but it doesn't. So this one doesn't do segment fault. Doesn't mean the buffer you should override is 70. 71. What's 71? 71 is like you override the full.
No, that means I override 1 byte of return address.
No,
One extra. No.
That means that yeah, there could be a lot of coincidence there. For example, you override 70 bytes. What if the 71 byte doesn't matter or something? You know, there could be some coincidence. That's why we need to check the object dump to say the exact location.
Got it. But the 71th byte is like the highest. It's the highest order byte, correct? So if it changes slightly, it should break. So if I even put like 70, if I put B, this should break, but it doesn't do segment fault. But
you are changing the least significant. For example, can we try? Let's try. Just put 0 there. Let's put hex 0 instead of.
Oops. Is this correct?
0, 0, 0, 0, I guess.
0, 0.
Yeah. We're probably to debug to find out why. Maybe that EBP is not used. But I will not rely on what I'm saying is I will not rely on this. I will always rely on the object dump. I will rely on the code.
Okay.
Yeah, you can try.
I'll just.
Sure. Another way is you can use GDB to debug this. It doesn't necessarily give you a share with set UID, but you can make sure it works.
Okay, let's maybe then let's do GDB way and just
yeah.
Oops. Let's do GDB.
You probably want to copy what you have there.
Am I not running this right? Like this? Okay.
Yeah. Yeah. Do you have that? Still have that Python thing there? You want to copy it here?
Yep. So I guess I do 4 for now. So we just look at.
Yeah, you just do the The one with the exact location, the exact address, you have
Yep.
one? No. You need the whole thing, Python. You need
Oh,
the
yeah,
whole thing.
Python say. Okay.
Yeah.
And I guess can I just do this thing again? Oops,
So,
like
so
this?
no, this one, no, you can't do that. This is
Yeah.
gets or something. What is the variable gets, right? You need to do R
R.
space bar, white space, then three, the, less than sign. No, this is not argument.
Mm-hmm.
The less than,
Less than.
like the arrow,
Oh,
to three
okay.
of those. Three of those, you need three of those, yeah.
3 of those. Okay.
Then you put a dollar sign. No, you need to use a dollar before
Dollar. Yeah.
Python, yeah. Yes, and you do this.
Okay.
Yeah, you do this. So you probably want to debug this. Oh, there is something wrong. There is a C there. Do you see that? At the end of it,
Up.
you need
Yeah.
a double quote. Yeah. Oh, you didn't quote it. You need a double quote there. Yeah. Okay. So, see,
Okay.
obviously you jumped to some share code, but probably the wrong address or something, right? You're close. You can see the address you get is a D6A0. It somehow go to D70D. Looks like it jumps there. So why don't you just set a breakpoint? Yeah, set a breakpoint maybe there. Then do that again. Then let's do step by step. After we, yeah, let's just do return to see where we get to.
Okay.
So you don't have to type it every time. You just enter. It will
Enter?
do yeah, it will
Okay.
do that. So where are we? We're going to 7D. Let's go to 7D. Just keep going. Okay. And one more time. Yeah. We're here. Then we could return. Let's say where we're going.
I think I did. Oh, okay. Okay.
Yeah. Now we're in D6A0. Okay. Try to disassemble from there. Do a X. No, you cannot do disassemble. You have to do X. Yeah. Then do like maybe 50i, 5i, 5i, 50i. So yeah, that's okay. Ooh, so that's a problem. So this is not valid instructions. Somehow we didn't override it to the correct address.
Is this even, where is this? Do we have this? I
Is
don't
this
think we
the-
have this, no.
Yeah, you didn't give this address. So there is something off. Yeah. We're trying to figure out because can you show the Python command you provided?
Yeah, let's, okay,
What's-
let's, oops, not this.
Yes, so the address you give is the address you give is D6A0. Okay. Just to do D675 because we know it's 75. Yeah. Do 75 here. Yeah. Do this one. Okay. Then maybe
I could do this probably. I could just,
yeah.
okay,
Wait.
so then I do,
Let's do yeah. You need to one more step. You need to return. You didn't return here. You
okay,
need to NI here. Okay. Now disassemble from here. Okay. This is
Okay.
correct. Okay.
all right.
So if you continue here, you are executing the share-code, but it may not give you the, yeah. So say, can you try to type something? You did execute the share-code, but it doesn't give you the, because it's a set, I'm not sure if you can debug a SetUID program.
Yeah, I don't, yeah, I think I,
Okay.
let's,
So-
let's try this, run this one then.
Yeah, so this one is correct. The only thing you need to config is somehow find a address. You need to hit that 39 slot, or you can use the second approach we used there. Remember, you have a huge slot. You have a huge knob select.
Okay,
That can increase your chance. Yeah.
yeah, okay.
Yeah. Okay. Let me ask everyone else. So, do you guys need anything? What's the status there?
Oh, I got a show, I think. Oh, did I? No. Yes, I did. No, I did not.
So,
I have no idea.
Charles, we check. Is everything good?
Yeah, just had to look after my kids for a few minutes. So, but I'm working on it.
Okay. Yeah.
Sorry.
Okay. Let's say, Sai Yashwant. How are you doing there?
I just have to go through the video again, Professor, but I'm following what ABIC is doing right now.
Okay. How about Srini Kath?
If I am doing okay, I'm like, I guess trying
Okay.
different things.
Okay. Jackie, are you an undergraduate?
I'm a grad student.
Okay. So how are you doing there?
I am working on it right now, but I followed everything up until this point.
Okay, cool. Okay, I guess that's it for today. So I will post the video soon, all the code and also the homework. Cranking this behemoth level 1 is one of the homework. Okay, cool. So I guess this homework will be a little bit more difficult than the previous two, and it will just getting more difficult from now on. So, okay. If there is no, yep.
Do you
Question?
think there could be an ASLR enabled here?
I cannot see your screen here. Let me see.
Oh, I was asking, could there be ASLR enabled here?
No.
No?
There's no.
Okay.
Yeah, there is no. Yeah, you can run them multiple times. You can say they have the same address. So yeah.
Okay.
Mhm.
Oh,
Okay.
yep.
Okay, cool. See you guys next week. If you have any questions or if you need to visit my virtual office hour, just ping me on Slack or shoot me an email, and we can schedule a meeting together. Okay, cool. Bye, guys. See you next week.
Have a good one.
Bye. See you next week.
Thank you.